So let's look at some basic properties of fluids. So let's say I have a tank and it's filled with some fluid, for example water. One other thing I should note that I didn't really talk about in the first video is that when we talk about fluids, we're not just talking about liquids. We can also talk about gases in a very similar way. And so let's say for this fluid that we have, it has cross-sectional area A, and there's some force F that's being applied to it. Okay? Well, we know that density, which we'll write as rho, is equal to mass over volume. Okay? Now we define pressure P is equal to force divided by area, where again area is A, it's the cross-sectional area, it's perpendicular to where the force is being applied. Okay, so now let's look at an application of this. So let's say we look at some volume of the fluid in the container. Okay, so we'll look, in this case, we'll look at a cubic volume. Okay, this volume is going to have area A as its cross-sectional area on top, and it's going to have a height h. Okay, so the volume of this is just h times A. So we're going to have, if we look at the forces on this, we know that all of the fluid and everything on top of it, there's going to be a force Ft pushing down on it, the force from the top. We know that we're going to have gravity, right? Gravity is going to be at the center of mass. It's going to be the mass of this fluid times g. And then we know that we're going to have a force from the bottom, which is going to be, you know, all of the pressure, all of the fluid and everything on the bottom pushing back up with the force B. It's, you know, you can think of it as kind of a normal force if you like. So we have gravity, we have kind of a normal force of things pushing from the top, we have a normal force of things pushing on the bottom. Of course, we also have, you know, a force from the left and a force from the right, which are the normal forces, you know, of the fluid on the left and right sides. But just to keep the picture a little simple, we'll ignore those now. We'll ignore those for now because we know that those are just going to cancel each other out. So we'll just look at the fluid in terms of this. You know, just the vertical forces, right? So so if we look at our net force, we see that we have a buoyant force. The force from the bottom pushing up. We have a minus force from the top pushing down. We have a minus force of gravity. And we know that equals 0 because, you know, once again, we're looking at a fluid that's not moving, so it's in static equilibrium. So this tells us that gravity is equal to the force from the bottom minus the force from the top, or in other words, the force from the top. The force from the bottom is equal to, you know, is equal in magnitude to the force of gravity plus the force from the top. Okay, so then going to our formula, pressure equals force over area. Area in this case is just going to be A. So the pressure at the bottom is going to be the force at the top over A, which is just going to be the pressure at the top plus, so I'm going to rewrite our mass as rho times V, where the volume in this case, so we have the density of the fluid, and then the volume is going to be h, the height, times the area A, times G, but now we're dividing by A. So we see that this is the pressure at the top plus rho G H, where of course we note that H is going to be, if we define this as Y at the bottom, Y at the top, then it's going to be Y at the top minus Y at the bottom. Okay, and so this is Pascal's law, just that the pressure at the bottom is the pressure at the top plus rho G H. So notice it doesn't matter the shape of the container, it doesn't matter the shape of this object, it doesn't matter how wide it is, it doesn't matter what the area is. All we care about is the pressure at some point in a fluid is going to be the pressure at some other point plus the density times G times the difference between the heights. So it's really a function of the height, the initial pressure, and the density. So if any two of those aren't changing, then that allows us to see which parameter is changing with the pressure, or if the pressure is just the same. Okay, and so we can notice one more thing. We can say at the surface, well, pressure at the top would just be atmospheric pressure. And so it's rho GH. So this is telling us the pressure at the surface of a liquid is just atmospheric pressure plus density times G times the height above where we're looking at.